So our previous discussion on dimensionless numbers and dimensional analysis is important because of this idea of similarity. Basically what this means is that in order to be useful, experiments have to provide data that we can use to predict full-scale prototypes. So we want to make sure that our models that we develop based on data provided from scaled systems can actually be used to predict full-scale prototypes. And so basically what we want to be able to do is say, if we did some tests on our little toy bumblebee over here, we would be able to show that they also apply and will work for the full-scale guy that we see in the movie. So we have to be a little bit careful. And we do that by looking at the dimensionless numbers and the dimensionless ratios and the pi terms and so on to see how the two different systems are going to behave. So we have actually 4 different types of similarity that need to be satisfied. The first one is geometric similarity, which basically requires that your scale model and your prototype have the same shape and proportions. So the length to height ratio and arm length to height ratio are going to be the same for the model and the prototype. So like a 1/100th scale model would have geometric similarity. Now this doesn't depend on any fluids or flow rates or anything, so it's often the easiest type of similarity to achieve. Kinematic similarity means that your velocities differ everywhere by just some constant factor. So what that means is the velocity everywhere in your model is half the velocity in your prototype. And this comes from the continuity equation, so there's no particular dimensionless numbers that need to be satisfied, but it does require geometric similarity. So if you don't have geometric similarity, you can't have kinematic similarity. Dynamic similarity means that the forces differ by constant factors. So if the drag force is half in the model, then the lift force should also be half in the model. And this is typically the most restrictive scaling requirement for scale models. It comes from the momentum equation, hence the forces. And you do have to consider all the forces that are important for the flow, so it can be a significant challenge. Thermal similarity comes from the thermal energy equation. It basically means that temperatures and heat fluxes have to be similar. The problem here is that in model studies, similarity may not be possible for all cases. What I mean by that is if you look at the Froude number and the Reynolds number in the dynamic similarity case, if you look at Froude number and compare that to length scale, and you assume you're still on planet Earth so that the two G's are the same, you can derive that the velocity of the model divided by the velocity of the prototype is related to the length scale of the model and the prototype. And if you substitute this into the Reynolds number, you can get that the kinematic viscosity of the model divided by the kinematic viscosity of the prototype is the length of the model over the length of the prototype to the power of 3/2. Now, at first, this doesn't necessarily seem like it's such a big problem, but if the length scale is 1/100, then the velocity scale is going to be 1/10, and the kinematic viscosity scale is going to be 1/1000. So this is a problem. It's also a problem because we typically test using the same fluid as our prototype. So if our prototype is going to operate with water, we test with water. If it's going to operate with air, we test with air. So that means that the kinematic viscosity ratio is going to be 1. So that's not going to be satisfied. So it's actually usually impossible to satisfy both Froude number and Reynolds number similarity. So we have to use our engineering judgment to decide which one is more important for a particular application. Now, some simple phenomena can be modeled analytically to overcome incomplete similarity, and this may actually require you to have some adjustment to your experimental results. However, this should be a scientific adjustment using carefully determined equations. You can't just change the data to fit what you want it to fit. You have to have a method and an equation that says we're gonna apply this correction to the data to account for this phenomena so that we can isolate one thing from the other. We also should use careful experimental design to minimize the effects of these scaling distortions.